Hi, good morning.
Good morning, sir.
Yeah, good morning. Okay, so till yesterday, we finished module 2, and module 1 and 2 were completely based on the ARM microcontroller design and how to code the ARM microcontroller using the assembly language. Okay, these are the things that we understood in the module 1 and 2. And now the end of module 2, so you have the idea, and even we have completed all the part A programs also. So with that, so you people have got an idea or the knowledge of how to program the ARM microcontroller using the assembly code. So now from module 3, so we are not going to write any assembly code. So we're not writing any assembly code, but part B lab programs, we instead of assembly code, we go for writing the embedded C code. So now our focus will be on understanding the embedded systems. So introduction to embedded systems. Now before we understand what is an embedded system, okay, so first we'll try to understand the definition of the system. So after understanding what is a system, then we'll try to understand what is embedded system. So that is what I'm starting now. So first, what is a system? So system can be any device, okay, any device which can do one or more tasks. So based on the set of rules. So that is what we call it as a device. Okay. A device that performs one or more tasks according to a fixed set of rules, we call it as a system. You can give many examples. So many examples for physical devices. Okay. Even your desktop or the laptop is also a system. We call it as a computer system, laptop system. Okay. Now what they do, they perform one or more tasks based on the set of rules. So similarly, so not necessarily the physical systems. You can take the education system. We call it as again system. Government system. So why? Because it performs, again the government also performs multiple tasks, so based on the set of rules. Even the education system also performs many tasks by following the set of rules. So a system is a device that performs one or more tasks according to fixed set of rules. This is one way of defining the system. And what is the other way of defining the system? So you can also define a system as a collection of interrelated components. Okay, it's a collection of interrelated components and that work together to achieve a common goal or a common purpose, or to achieve one or more tasks. Okay, system is a collection or integration of interrelated components, and all these interrelated components has to work together to achieve a common goal. That is what a system. You take the example of the desktop systems. Again, it's a collection of interrelated components. You have processor, you have RAM, you have hard disk, keyboard, monitor, all these things. So when they are integrated, so with a specific set of rules, okay, so they perform a common task or achieve a common task. If any one of the component is not functioning properly within the set of interrelated components, so it is not possible for the system to provide all the required services. Okay, so a system is a collection of interrelated components that work together to achieve one or more tasks, and that is the system. Okay. Any device, any physical device you can imagine. Okay. Even the bike which you use in order to travel from home to college or college to home is also a system, because even it is also a collection of interrelated components. When all those interrelated components are working together, so it provides you some service, some kind of a service it provides. And what service it provides? It provides you the transportation service. And similarly, when all the components of the computer systems are integrated and they're working together, it provides you the service. So the service which you require is provided to you. Okay. Hence, we say a system is a collection of interrelated components that work together to achieve one or more tasks. So either you can go for defining this way or this way. Both are correct. So people understood what is the meaning of system. What is a system? Is it
Yes, sir.
clear? Okay. Now, so with the understanding of the system, so now we'll move on to the next thing. Okay. Embedded system. What is an embedded system now? So definition of the system you already know. Now what is an embedded system? Embedded system, it can be either an electronic or electromechanical system. And again, which is designed to perform a specific function. So here we said one or more tasks or one or more functions. But here the embedded systems are designed to perform a specific function. Okay, so embedded system is either an electronic or electromechanical system which is designed in order to perform a specific function using a combination of both hardware as well as firmware. Even for the embedded system, you require the hardware. What kind of hardware components are required? So that you people already know. So because in the module 1 and module 2, we have covered through the important components of the what embedded system. So memory it requires a microcontroller, many other peripheral devices. And along with that, you also require a firmware. So why it's called as a firmware? Because it is the one which is permanently stored inside the ROM, read-only memory. For embedded systems, so the software cannot be changed. It is a firmware. It is a permanent one which is stored inside the read-only memory. And that software is going to control the functioning of all the hardware components which are within the embedded system, and that is going to guide how all these hardware components should function in order to get a specific task done. Okay, so this is what the definition of the embedded system is. Okay, and why we say it is either an electronic or electromechanical system. So sometimes an embedded system which you're using is purely electronic, which doesn't have any mechanical parts connected to it. So sometimes even embedded system can also go for having a mechanical system as well. So majority of the devices which we use in the agricultural lands, so with the advent of IoT, Internet of Things, so we are using majority of the devices even in the agricultural land. So it may be a simple what is that called as a sprinkler system. Okay, so again, so we have an electronic device which is running a firmware, and what it's going to control, the functioning of all these sprinklers. So how much it should rotate, when it should stop, all these things. And then again, I have my embedded system connected to a mechanical system, and my mechanical system is under the control of an electronic device. An electronic device is controlling the mechanical parts. Okay, so and everything is automated, so we don't have to do anything manually. Okay, so this is what the definition of an embedded system is. Next, now examples of the embedded system. What are the examples I can give for the embedded system? So we have this industrial robots. Say what is this industrial robot is? So you can assume this as a packing robot. Say an industry is manufacturing several items. Okay, and all those items needs to be packed. So per minute the industry is able to manufacture 1,000 such items, and all 1,000 items needs to be packed. Instead of using the manpower for packing, so 1 minute it is able to produce 1,000 objects. Is it possible for one single human to pack the 1,000 objects? So it is not possible. So instead you can go for using an industrial packing robot system which will go for packing 1000 objects per minute. So just we have the objects getting manufactured and they're flowing on the conveyor belt, and we have this industrial robot, packing industrial robot standing in front of the conveyor belt. Every time it sees the object flowing on the conveyor belt, picks it, packs it. Okay. So a lot of manpower you can save. So industrial robot. Then this is another example. So GPS receiver is another example for the embedded system. And this industrial system, again, a robot, what it can do, it does only a specific job. What is its job? Only packing the objects. Can it do any other task apart from that? No, it cannot do. That is the reason we say an embedded system is either an electronic or electromechanical system which is designed to perform a specific function. Now this industrial robot is an electromechanical system. So because all we have these bearings and these motors which are connected here, the motor is also necessary, stepper motor. Either it could be DC motor. All these things are controlled by using the microcontroller and the firmware software which is running. Okay. Hence we say they perform the specific task. And this is GPS receiver. So which is designed for only one specific purpose, that is receiving the GPS signals. Then digital camera is another example. Okay, so what is, again, this performs the specific task. What is that? Capturing the images and then storing. So DVD players is another one. So wireless routers, MP3 players. So we don't have separate MP3 players devices these days. Nobody carries. So all of us use our smartphones as what MP3 players. TV setup boxes, gaming consoles. So photocopier, your Xerox machine is also an embedded system because there is a microcontroller inside it. So even inside the microwave ovens, there is a microcontroller. Now, all these things are embedded systems. Okay. So and then again, this all these devices, so they're not just embedded system. Even you can go for making them smart embedded systems. Okay. So with the concept of Internet of Things, so even all these devices can be made as smart embedded devices. Okay. So that means without the human intervention, all these devices can be operated and controlled. So not within the specific area, even sitting at the remote place, it is possible for you to operate and control all these devices. So if you're able to operate and control all these devices sitting at remote place, it is called as what? Internet of Things. And this Internet of Things can also be made smarter. Okay. Now how you can make it smarter? So because all these devices, so you can make them to uh, send you the alert messages. Okay. So it all depends on how intelligent embedded firmware software what you're writing. Okay. So you can make your firmware more intelligent and respond quickly, and all these devices can give you the guidelines. Okay. And every embedded system is unique in nature. Okay. And why we say it is unique in nature? Because the hardware and the firmware that is used in each of the application domain varies. Say for example, I have uh, this wireless router. So the microcontroller and the firmware which is running here is different from the microcontroller and the firmware which is running on the GPS receiver. So in that way, so all embedded systems are unique in nature. And then embedded systems are becoming inevitable part of our life. And these are the devices which are making the ubiquitous computing possible. What is that ubiquitous computing is? So what ubiquitous computing says is, so computing is everywhere now. When you're sleeping, so there is the computation happening. So smart watches which you wear, so they're doing the computation. What computations they do? So they tell you when you wake up, this is what the time. So you slept for these many hours. That is what it says. And even when you're sleeping, your smartphone keeps receiving the WhatsApp messages and keeps receiving the email messages. All these things. Okay. So inevitable part. So, and these embedded systems are making the ubiquitous computing possible. The computing is everywhere. Even when you are traveling, you can do the computation. So once upon a time, so we used to do computation only when we're sitting in front of the desktops or sitting in front of the laptops. Even when you're in kitchen, cooking something, so there is what the computation happening. So even when you're driving, there is some computation happening. Okay, so competition is everywhere, and any product or equipment in all fields, including say household appliances. So you can list majority of the embedded systems, for household appliances, and few of them were listed here. So there's microwave oven, okay, and then you can list your washing machines, refrigerator, and many more things. Even the bulbs are also what the smarter bulbs these days. Okay, so they are able to detect the movement, and then so when you're inside the home, the bulb gets turned on, and even if it will also check the um, brightness of the natural light. If that itself is sufficient, then it goes automatically off. So even the bulbs are made smarter. Okay, and then so we have in telecommunications, so medical equipments. So I guess you people have noticed. So majority of the medical equipments are embedded systems, and these days, okay, I think in every home, so there is this oximeter, okay, because of Corona. So majority of the houses have taken their own oximeter. What is it? It is again an embedded system which has a microcontroller and the firmware running in it. And there are many medical equipments, from very small medical equipment to very big, okay, medical equipment. Okay, and then industrial control systems. So I told you one example here, that is industrial robots. So like this, you can go for having many more industrial control systems, and then the consumer products. So you cannot list a domain where the embedded systems are not available. So embedded systems are available everywhere. Okay, and even we are using an embedded system. Your phone is also an embedded system, because it is all majority of the smartphones and iPhones are based on your ARM controller, ARM based microcontrollers. Okay, and so again, smartphone or iPhones are inevitable. So we cannot leave a single day, not even single day, 1 hour we cannot spend without our smartphones or iPhones. Okay, so they have become so the inevitable part of our life these days. Okay, next. Next, so you understood the definition of the system, two definitions of the system, and then the definition of the embedded system. So now, how IEEE defines the embedded system? So it defines like this. The embedded system is a device that is lodged in other systems. Okay, so you can say it is lodged in other system, or that is housed in other devices, and what it performs one specific task. So device that is lodged in other systems. Now what is the device that is lodged in other systems? So it's a microcontroller with a firmware software. This is what is lodged or housed in the other systems. Why we are lodging or housing the microcontroller and a firmware inside the other system? Just to make the other system, inside which the microcontroller, the firmware is embedded, to control. Now the complete control of the system will be done by the firmware software which is running within the embedded system. And by running, what it can do? It can do some kind of a specific task. Now here is a simple diagram. So very high level diagram which is shown over here. So this is what the embedded system is. It has two things. So my software components, usually this is the firmware and then the hardware components. And what my software components are going to do, so they control how this hardware component should be used in order to perform the specific task. And it takes the system input from the user, perform the specific task, and when the input is given, the software components knows how this hardware component should be utilized for performing the computation. Once the computation is done, it produces the system outputs. So this is the very high level diagram that we are understanding. Okay, this is how the IEEE defines the embedded system. So which one to write, whether this definition or the definition which I told earlier, anything you can write. So both mean the same thing. Okay, just saying it's an electronic or electromagnetic system, electromechanical system, which is designed to perform a specific function using both hardware and firmware. And what this is saying is, so it is a device that is lodged in other systems and performs a specific task. Next, so time to understand the characteristics of embedded system. So what are the important characteristics of embedded system? So one is limited memory. So embedded systems have limited memory because they are the small handheld devices, battery operated devices. You cannot have a bigger memory to them. So you can ask me a question, sir, the memory now it comes in the smaller chip, very smaller chip. Even so, say bigger memory like 250, 500 GB or even terabytes comes in the form of a smaller chips. Why it is not possible for adding a bigger memory to the embedded systems? So bigger the memory, so the power consumption increases. Why? Because as the memory locality preference increases, even the search time also increases. As the search time increases, the energy should reduce. That energy here is nothing but the power. So as the search time increases, there is more power consumption, and the battery life will go down soon. Okay. So limited memory, that is one important characteristics of the embedded system. So all embedded devices, they have limited memory. And then also limited peripherals. So you cannot have too many peripherals connected to the embedded system, because if I say too many peripherals I need to connect, you require more I/O ports also. Okay, and I'm already saying these embedded systems are the small handheld devices. So how many I/O ports you can provide for the embedded system? So again, the number of peripherals which you can connect to the embedded systems are also limited. And then should be designed to operate at the lower power. So this is another important characteristics of embedded system. When you're designing, you design in such a way that it consumes very low power for operation. So for that reason, so this ARM microcontrollers, all ARM microcontrollers are called as LPC. So low power controllers. Even R, a microcontroller which is based on ARM7 design, that is 2148, is called as what? Low power controller. Low power controller 2148. So this is the number of the microcontroller which is based on the ARM7 design. Okay, LPC 2148. Next, should be designed to be highly reliable, stable, and safe. So we have again in embedded systems something called as critical systems. Okay. So what are critical systems? So I can give you a few examples. I've already told you those examples. Say heart pacemaker. What is it? It is again a medical embedded system, which is a very small system built into the human body for stimulating the heartbeat. So this I call it as a critical embedded system. Why we call it as a critical embedded system? Because if something is not proper, so then there is a threat caused to the human life. Okay, and then similarly, insulin pump system is another what? critical embedded system. Okay. ABS, so auto braking systems, which are used inside the vehicles. Okay. So is also a critical embedded system. So that means, so they should function at the right time and the proper time. And the failure rate of such systems should be very less. If I say a heart pacemaker and the failure rate of the heart pacemaker is very high, then then there is always a threat to the human life. So it must be made reliable. How to make it reliable? The failure rates must be very low. Okay. So failure rates. So say bank ATMs you take. If the failure rate of the bank, say if the bank ATM, so it is installed up and running, and if it functions successfully without any problem, without saying out of service for the next 1 year or 2 year, then you say it is highly reliable. If the bank ATM fails every day, say for example it fails every day, then you don't call it as an highly reliable one, so it is an unreliable ATM. Okay. Then it must be stable. So the critical embedded systems must be stable, and then they must be safe. They should not cause threat to the human life. So, example, the heart pacemakers, insulin pump systems, okay, the ASP, all these things. In a airbag control system, everything are critical embedded systems, and they should be designed to provide higher reliability, stability, and safe. And so they're designed to perform the specific function or a task. So you cannot perform the general purpose computations here using the embedded system. So what you can perform is only a specific function. And then, so minimum user interface and complicated UI or complicated UI. So majority of the embedded systems are small devices, handheld devices. So they themselves are small, and you can just imagine the display panel in those devices. That is again small. Now, how do you go for writing an UI user interface for such complicated display panels or very small display panels? So you can just imagine writing an UI for the desktops or the laptops and writing the same UI for the handheld devices. So writing it for the handheld devices is very complicated. So because the display panel is very small and it is not possible for you to write the menus and the drop down boxes and all these things, all the UI elements which either it could be a simple text box or a button or the menus, all these things. So it is very difficult to accommodate within a single, very small display panel. That is the reason we say minimum user interface in complicated UI. So developing or designing an UI for the embedded system is a challenging task. So because of its uh, what display size limitations or constraints, and should also meet the real-time constraints. So again, while explaining in the previous modules, I mentioned the operating system that is used inside the embedded system is called as what type of operating system it is?
Real-time operating system.
Real-time operating system. So within the embedded system, we use the real-time operating system, and again, there are two types of real-time operating system. What are they? What are the two types of real-time operating system? Hard real-time operating system and soft real-time operating system. So all the critical embedded system which I mentioned, okay, critical embedded systems like heart pacemaker, insulin pump system, and ASP, so they will be running the hard real-time system. So where there is a rigid timing constraints. So if there is a task which should be run at some time and complete its execution at the designated time, so it should start at that time and it should complete its execution within that time, and no delays are entertained. Okay. So and all the embedded system, they should meet the real-time constraint. And some embedded system should go for meeting the hard real-time constraints, and some the soft real-time constraint. And I gave you the example of TV setup boxes for the soft real-time constraints. So why I said it as soft real-time constraint, because so the when you're designing the setup boxes, they got to be designed, or the microcontroller which is there inside the TV setup boxes, it should go for receiving 22 to 30 video frames per second. So if it is capable of receiving 22 to 30 video frames per second, so then the video quality that is displayed will be good. So if for some reason if it is not able to receive 22 to 30 video frames per second and play it for you, so then the quality, video quality is distorted, and this is not going to continue forever. So you may get a distorted video quality for say 2 seconds or 3 seconds or maximum 10 seconds. Okay, and after that it comes back to the normal position. But this 2 seconds and 10 seconds delay in the critical embedded systems like heart pacemaker and insulin pump system and ABS, so will cause a severe damage. So that is the reason we say some embedded systems, they require the hard real-time constraints, and some so soft real-time constraints. When I say soft, some what delays can be there, some relaxation on the timing constraints will be there. And the last important characteristics is that they should be dependable. So what is the meaning of dependable? So they should not cause threat to the human life, or damage to the environment, or economic loss in case of failure. So if any embedded system is failing, it has to fail safely without causing so threat to the human life, damaging the physical surrounding environment. So we should not damage the environment, and also it should not cause the economic loss. Okay, so that is what is dependability. Okay, so these are all the important characteristics of the embedded systems, and if you're an embedded system designer, you should take care of all these characteristics while designing an embedded system. Hope you people understood till here. Is that clear till here? Any doubts? Please talk. Hello, can you hear me? One of you unmute and talk.
Yes, sir.
Yes, sir.
Okay, thank you. So these are the characteristics of the embedded systems. So next. So now time to look into the differences between the embedded systems and the general computing systems. Okay. So when I say general computing systems, it is your laptops or the desktop systems. When I say embedded system, any Android device. So starting from your phone. Okay. Now we'll see what are the major differences. So first we'll understand with respect to the contents. So general purpose computing system. So it is a system which is a combination of generic hardware and general purpose operating system for executing a variety of applications. So the operating system that is running on the general purpose computing system, we call it as POS. So platform operating system. Okay, and it is a general purpose operating system. So on that operating system, you can go for running a variety of applications. So not one kind of an application. Now you can just imagine your laptops. So we don't have one application running on it. So we go for running multiple varieties of applications. Okay. So, and then coming to here in the embedded system is a combination of special purpose hardware. Okay, it is not a generic hardware. Generic hardware in the sense a general purpose hardware. Now this is a specific hardware, specific purpose or a special purpose hardware, and an embedded OS. So real-time operating system, either hard real-time operating system or soft real-time operating system. for executing only a specific set of applications. Sometimes it runs only one application, and sometimes it could be a set of applications. Even we cannot say it runs only one applications. So some embedded systems are designed to perform the execution of a set of applications also. So but general purpose computing system, so they can go for performing the execution of a variety of applications. Next, OS, coming to the OS. So this is with respect to the content. So here we have generic hardware, here we have a special purpose hardware, here we have a general purpose operating system which is capable of performing the execution of a variety of applications, and here we have an embedded OS for executing a set of applications. Okay. Next, OS. So it contains a general purpose operating system, GPOS. It contains a GPOS, general purpose operating system, or sometimes you can also call it as POS, platform operating system. So just POS. Okay. And then the embedded system, so may or may not contain an operating system for functioning. So you'll understand later. So it's not necessary that all embedded systems should have the operating system. So a few embedded system will not have the operating system. Only there will be a small bootstrap code, and then we have the firmware, and that is going to control the functioning of the firmware execution of the embedded hardware. So not all the time. So we require operating system for the embedded system. Sometimes an embedded system can be even without the operating system. Okay. Next, alterations. Okay. So applications are alterable. So here, any application, say for example, I can write my own program. Okay. So as I require, so as per my requirement, I can go for developing my own program, and any number of time I can go for altering my program and running it. And that is possible in case of general purpose computing system. It is possible for the user, for the end user to reinstall the OS and also add or remove the applications. So that is what we do on the general purpose computing system. So you any number of application, if some application is not required, we uninstall it, and some application new application is required, we bring and we install it. So all these things can be done any number of times. So but what happens in an embedded system? The firmware of the embedded system is pre-programmed. That is the reason we say it is firmware. It is pre-programmed and already permanently written into the ROM, read-only memory. And it is non-alterable by the end user. And this is also one reason why we say it performs only a specific task or a specific application. Okay, so only the program, so the application for which the programmed program is written, only that task the embedded system is able to perform. Next, what we have is a key factor. So performance is the key factor deciding is the key deciding factor in the selection of the system. So whenever I want to select buy a new general purpose computing system, so either it could be a desktop system or the laptop system. So what we do, we always look for the performance. Okay, and we always go for buying one such system which is faster. Okay, always we go for choosing the system which has better performance. That is what we do. So here, so we look into the application specific requirements like performance. Along with the performance, we go for looking into this power requirements also, memory usage, okay, etc. The key deciding factors. But here, when you're planning to buy a general purpose computing system, okay, so we don't look for the what power requirements. So our focus will be only on the performance. Now, when I say an embedded system, performance, power requirements, and memory usage, all these things are the key deciding factors, before I buy an embedded system. So for example, whenever we buy the smartphones, we definitely ask its power requirements. Okay. So if you charge today, so it should be able for you to use the phone for the next 24 hours without charging. So because all these days your smartphones and iPhones, so they're connected to the internet all the time and they keep consuming a lot of power. Next, power consumption. So here more and here it is less. So they're designed to consume less power. And then the response time, so not critical. So even if the general purpose computing system are not providing the rigid response time constraints, so is okay, okay, not a major issue. But here, the embedded systems, so it is critical for some applications. So as I mentioned, few applications like the heart pacemaker, and then insulin pump system, and then ABS, auto braking system. For all these things, the response time is critical. That means the response time must be properly attained. And execution, so need not be deterministic. What is this? Deterministic. So every time I execute my general purpose computing system, so if it produces the same kind of output and if I'm able to predict this as what I get, then I say it is a deterministic system. Okay. And most of the time, the general purpose computing systems are non-deterministic, whereas the embedded system is deterministic. So why it is deterministic? See, like hard real-time systems. For hard real-time systems, say this function one, so starts its execution at 0th millisecond and it must complete its execution on second millisecond. So it is deterministic. So if it starts at 0th, I can say it is a total execution time is 2 milliseconds. If it starts at 0th, it completes its execution at the what second millisecond. So if it starts at 10th millisecond, it should complete its execution by 12th millisecond. So that is guaranteed and that is determined. So but in case of the general purpose computing system, it is non-deterministic. Say the execution time for a process is 5 milliseconds and it is starting execution at 10th millisecond. So we expect it to complete by 15 millisecond, but that is not necessary. So it may not happen in the general purpose computing system. It might take more than 15 milliseconds. Okay, because scheduling comes into picture because we have here the scheduler scheduling too many processes for execution and that may delay the execution of the process. So even though its execution time is 5 millisecond and started its execution at 10th millisecond, so it might get delayed. So and it might complete its execution at the 20th milliseconds or 25th millisecond. But in the hard real-time system, the response time or the execution time is always deterministic. Okay, so if I have a task to be done and if it requires 5 milliseconds of execution and if it is starting its execution at 10th millisecond, so it will definitely complete its execution at 15th millisecond. So people are able to understand.
Yes, sir.
Okay, so these are the differences between the embedded system versus the general computing systems. So next is the history of embedded systems. Okay, when all this embedded system they started, so they even started before the IT came into picture. So embedded systems were existing before the IT had its place in the market. Now initially, what kind of devices were used in designing the embedded system? The kind of devices that were used in designing the embedded systems were vacuum tubes. So even so once upon a time, that is during 1945, 1944. So these were the major components of the computer system also. Vacuum tubes were the major components which were used in building the computer systems during 1944 and 1945. These were the major components. Now these days, so all these vacuum tubes they are replaced by the transistors and diodes. We have transistors and diodes. All these vacuum tubes they got replaced by the transistors and diode. And again, inside the integrated circuit you find millions and billions of the transistors. Okay. So initially these were the devices that were used in designing the embedded system, and they were programmed using the low level programming language. Okay. And this was the first modern embedded system, that is Apollo guidance computer was the first modern embedded system developed by Charles Stark Draper at MIT in 1960. And in 1961, okay, Autonetics D17 was developed, and the first microcontroller based embedded system was designed, that is Intel 4004, or designed for calculator. Even your calculator is also an embedded system. Okay, and it used this Intel 4004, so which was a 4-bit microcontroller. Okay, so this is the history, and it's still continuing. So next, in 1970s, automobiles started using the microprocessors to control the fuel, air mixture, engine timing, all these things. Okay, so this is the history. Even during from 1970s, even automobiles started using the microprocessors. So the first microcontroller, so that is TMS 1000, was developed in 1974 by Texas Instrument. And then this microcontroller consisted of the RAM, so built-in RAM, ROM, and clock circuitry. What is this clock circuitry? So as I already mentioned you people, for a microprocessor microcontroller to perform any task, what it requires is the clock cycles. So now this clock circuitry, which is containing the crystal called as quartz crystal, is responsible for providing all the clocking requirements of the microprocessor or the microcontroller. And later in 1980s, Intel started using this 851 MCU, a microcontroller unit, um, and yeah, sorry. So started using this Intel 8051 microcontroller unit inside the laser and inkjet printers. Okay. So in 1990s, small pager started. I don't know whether you people have seen these things or not. So I have seen these things. So 1990s, the small pagers came into picture. And next, in the year 2000, so the era of cell phone started. Okay, with the use many co-processors for signal processing. So digital signal processing. So 2000, from 2000, so the cell phone era started. So this is about the history of the embedded systems. Any doubts till here?
No, sir.
So definition of the system, two definitions, and then we went and understood the definition of the embedded system, examples for the embedded system, and you also understood all these embedded systems can be made smarter. So how to make them smarter? It is a program makes them smarter, and then we understood that all embedded systems are unique. Okay, so because what makes them unique, the hardware and the firmware makes them unique. And then we understood that embedded systems are making the ubiquitous computing possible. So that is computing everywhere. So computing while sleeping, computing while walking. Okay, even when the fitness app is also there, right? So that does the computation when you're walking. Okay, so when you're sleeping, when you're eating also it does computation. So because the calories, how much you're consuming, how much you're burning, everywhere computation is everywhere. Okay, and then when you're talking, there also the computation. Okay, next, and they have become the inevitable part of our life. And in the so next, say after 10 years, so these are the things which are going to rule the world. So all these embedded systems, so smarter embedded devices are going to rule the entire world. Okay, and they still make the world smarter and connected together. And this is what the IEEE definition that we went through for the embedded system. And what IEEE says is, So an embedded system is a device that is lodged or housed in other system to perform a specific task. And these are the important characteristics of the embedded system that we went through. So any embedded system you take, it has limited memory and limited peripherals. So as of now, so this limited memory, but in the near future, say after 10 years, okay, down the line 10 years, so this limitation may go, okay. So even the embedded systems so could support the memory in terms of what 500 GB or 1 TB, okay. And then low power consumption. All the embedded systems which are designing, they should be designed to provide high reliability, stability, and safe. So they should perform a specific function. And then, so designing the UI for an embedded systems is very complicated, and so they should meet the real-time constraints, either the hard real-time constraints or the soft real-time constraints, and they should be dependable. That means if any embedded system is failing, if it fails, it has to fail safe without causing any threat to the human life, without causing damage to the physical environment, and also without causing the economic loss. So, and then these are the differences between the general purpose computing system and embedded system that we looked at, and then the brief history of the embedded systems. Okay. So here we will stop. So let me take attendance. So we'll continue. So classification of embedded systems in the next class.